NPTEL lecture on earthquake resistant design of foundations. And today we are going to talk about 32nd lecture of this course, which is related to soil stone interaction. And today in this lecture, we are going to discuss effects of soil stone interaction. So as mentioned earlier, we are under the 5th module of this course, which is on SSI for deep foundations. And in this module, what we have chapters. First chapter was Introduction to SSI, which we have discussed just before this lecture, in 31st lecture. And today's lecture, that is effects of soil stone interaction, is in continuation to that. So we are at the second chapter of this SSI. And what we are going to talk today, let's discuss. When we talk about effects of SSI, then what we are going to talk is major effect of dynamic SSI. Then we have SSI systems. And in these systems, we are going to talk about direct and substructure methods. Then there are, in some cases, certain cases, there are beneficial effects of soil stone interaction, which is we are also going to discuss. And finally, we are going to talk about impedance functions, or that is called complex dynamic stiffness. So let's see what are the effects of dynamic SSI. But before that, whatever the information given in the slide has been already discussed in the last lecture. This is showing you seismic effect of presence of soft soil. What happens when the soil is present instead on the rock, or your structure is situated on the soft soil? Then control motion due to the effect of soil, it gets changed, and you get as a result what is called modified free field motion. Okay? So the product of control motion and effect of soil is modified free field motion. Then once you have effect of based on modified free field motion, for example, foundation, which is without mass or without considering initial effect, then what you get is kinematic interaction. When the kinematic interaction is applied on the structure with considering its mass, then what is lead to inertial interactions. So these were the steps of SSI, that is modified free field motion, kinematic interaction, and which we have already continued. In the slide also we have discussed in the last lecture what has been shown, that how systematically the effect soil is getting effect. First, there is no soil in the figure B on the top of it, which is called rock outcropping. Then in the C part, you have the soil on the top of it. As a result, your input motion get amplified, normally get amplified. The size of these arrows are showing the amplitude of the response, as we have already discussed. Now, when you insert this, the foundation and the structure without mass, that means without considering the inertial effect inside the soil, and due to this embedment, what you call is you have the kinematic interaction, and this due to the presence of kinematic interaction, you get the rocking component and significantly enlarged amplitude of translation component. Then once you consider the mass of the structure, once again the motion at the base of the structure get modified. You get a translation component as well as a rotation component, and the accelerations varies over the height of the structures. So these kind of effects we have discussed earlier. Now let's talk about here that how these effects can be summarized into different components. That is how the soil is playing its role. So these effects of soil can be described in 3 steps. Firstly, first the seismic input motion acting on the structure soil system will change, that is figure D. So the motion acting here, which is at the interface of the soil structure interface, shown in this figure, this is the soil structure interface, motion acting will be changed and it will be different than control motion. And the translation component will in many cases be larger than the control motion, and in addition a significant rocking component will arise for an embedded structure. So you could see you have a translation component whose amplitude is higher than the input control motion, and you have a rocking component. Each frequency component of the motion is affected differently, resulting in, for example, an acceleration time history which is quite different from the control motion. This amplification of the seismic control motion is held responsible for the fact that the structures which are founded on a deep soft soil have been damaged more severely in actual earthquake than have neighboring structures founded on rock. So what you could see that there is an amplification in translation component and rocking component. This amplification in the translation component or this of seismic motion that is held responsible for the structure which are founded on soft soil, they get more damage compared to those structures which are founded on the rocky sides. So if you have identical structures as we discussed in the last lecture, one is situated on the rock, another is situated on the soft soil side, then the response of both the structure will be different, and that is what we call the soil stress interaction. So this was the first effect of SSI, which can be treated as a effect of soil amplification. Okay. The second effect, what happens is the presence of soil in that final dynamic model, which is your figure 2E in this case, where you consider the structure, considering its inertia also. In that case, the presence of the soil will make the system more flexible because soil is flexible compared to the structure. As a result, there will be decrease in the fundamental frequency, and this decrease in fundamental frequency is generally significantly below the applicable for fixed base structure. So that means consideration, when you consider soil in the system, then the natural frequency of the system get decreased, and this decrease is below the natural frequency of the fixed base structure. And the implications of this reduction will depend on the frequency content of the seismic input motion. In certain cases, the fundamental frequency will be moved below the range of high seismic excitation, which results in a significantly smaller seismic input, which is normally felt by the structure. So what happens? The presence of soil will change the natural frequency of the system, and normally, due to the presence of the soil, the natural frequency of the system will get decreased, and when this the natural frequency get decreased, thus the modified frequency goes below the natural frequency of the fixed base structure. As a result, you may get the smaller response, as we will discuss later, for the reduced natural frequency, or it can be said, when you reduce the natural frequency of the system, there is an increase in the time period. So this was the second effect of the presence of the soil. Now the third effect, because the radiation of energy of propagating waves away from the structure will result in an increase of the damping of the final dynamic system. When we are going to discuss the wave propagation, then we are going to talk about that. In the soil, there are two types of damping. One is called material damping, another is called radiation damping. So regarding that damping, we will discuss in detail later. But right now, what you have here, that when the radiation of energy takes place due to propagating waves, then there will be increase in the damping of the dynamic system. And for a soil site which is approaching an elastic half space, this increase will be significant, leading to a strongly reduced response. So when there is increase in damping, response gets reduced. For a soil site consisting of a shallow layer, it is possible that no waves propagate away from the structure. If you have a site where you have only few layers, or thickness of the layers is very small, that means soil cover is very small. In that case, this increase in damping may not be significant, and in this case, only the metal damping of the soil will act, and no beneficial effect of the seismic response is to be expected. Now, in any soil stress interaction analysis, it is very important to determine for a specific site whether the loss of energy by radiation of waves can actually take place. So we need to understand if we can estimate that there is a loss of energy due to the radiation damping, whether it is there or not. It is reasonable to assume that the soil stress interaction increases the more flexible the soil is and the stiffer the structure is. So this is a very important statement here. So let me point out it here. This statement, it is reasonable to assume that the soil structure interaction increases the more flexible the soil is and the stiffer the structure is. So that means if you have soil conditions, when you have this, you have the soil conditions where this soil stress interaction will increase when you have more flexible the soil compared with the structure. That means the difference between the stiffness or flexibility of the soil and structure is wide. If compared to structure, if your soil is more flexible, in that case, effect of SSI is going to increase. On the other hand, it will be negligible for a flexible structure which is founded on firm soil. So these are the that regarding the effect of SSI. Now coming to this effects of SSI, which we have already discussed. Now the third, overall effect of dynamic SSI. So when we talk about overall effect of dynamic SSI, first of all, one need to understand there are many opposite effects. That is in general, what is opposite effect? One effect, soil amplification, is normally says that the response will increase, while the change in the natural frequency, the response may get decreased. Third effect is increase in damping also reduces the response of the system. So in general, what we can say that it is obvious that from many opposing effects, that is in general impossible to determine beforehand whether the interaction effects will increase the seismic response. However, if the first effect, which is the change of seismic input motion due to soil amplification, is neglected when the interaction analysis is performed, the response in many circumstances will be smaller than the fixed base response obtained from an analysis that neglects all interaction effects. So that means if you neglect the first effect, that is soil amplification, and you consider other effects, then in that case, most of the time it is expected that this response considering SSI will be smaller than the fixed base response where no SSI is considered. Now for this approximate analysis where you neglect the effect of soil amplification, the control motion is directly used as input motion in the final dynamic system. As shown here, final dynamic system is 2E. In this case, if you neglect the effect of soil amplification, then control motion can be directly applied at the base of the structure. But in that case, you will lose the effect of free field response and kinematic interaction. The fixed base analysis leads to larger values of the global response. For example, the total overturning moment and the total transfer shear, and thus to a conservative design. So when you carried out fixed base analysis, so it will give you the larger values of the global response, and once you get the larger value of the global response, that means you are carrying out the conservative design. Continue with the overall effect. Now economic consideration dictates that when the designing the structure, the reduction in seismic forces, approximate analysis is giving you the benefit in the design, then certainly that should be used. But one need to make sure that you have considered all the effects. There are some exceptional cases where the simplified interaction effect will govern the design. Further, it is important to stress that this approximate method of calculating the interaction, a method that neglects the free field site analysis and the geometric averaging due to the embedment effect, is inconsistent. For special structures, for example, nuclear power plants, SSI is always analyzed considering all effects. It is therefore true that taking the flexibility of the underlying soil into account when calculating the seismic response of a structure does complicate the analysis considerably. So what you have when you say the flexibility of the underlying soil, then in that case seismic response will be complicated. Okay, so this was the overall effect of dynamic SSI. Now when we carried out the soil stress interaction analysis, then it is assumed, many times it is assumed that soil behavior is assumed linear. And why it is assumed linear? It is to simplify the problem. And another reason is that also soil is mostly assumed linear, though non-linear consideration from linear soil is also possible. When you have the total solutions of the soil consists of sum of the response of the what is called free field and interaction effect. Therefore, nonlinearity cannot be considered until direct methods are used. So, interaction effect consists of two parts, as we already discussed. One is called kinematic interaction and another is called inertial interaction. And the third one is called free field motion, which can be found out using ground response analysis, or in short it is called GRA. Now continue with that, let's consider what are different soil interaction systems. SSI system, the soil consists of horizontal layers which are resting on a half space. And once you have this here, you have horizontal layers on half space. There are two components. One is horizontal layer, soil will consist of number of layers and on a half space. And both consisting of isotropic viscoelastic material with static damping. So here it is assumed that horizontal layers as well as half space is concerned of viscoelastic material, and in both the cases we consider static damping. The properties may vary with the depth but remain constant within the individual layers, and this structure can be embedded inside the soil. Here, what is half space? Half space is shown here. In case of half space, this is what we call the ground level here, surface free surface, which is called GL, ground level. Okay. And this half space is kind of a semicircle. It is a semi-infinite medium. Okay, so semi-infinite medium. Why we say semi-infinite? Because it is going to infinity in both horizontal direction, but in vertical direction it is going to infinity below. That means, but at the on another side you have free surface. So this is semicircle. You can say this, like semi-sphere, where this is like 3-dimensional. In 3D case, it will be semi-sphere, and once you have the semi-sphere, in that that can be said the half space. And the properties of this half space as well as the layers. You may have a number of layers with this. If you have layered site, so it will be layered half space. So you have a number of layers, and these are the 1, 2, 3 layers, and these are straight lines. Then you can say the layered half space, and it is assumed that properties of these layers are constant in the horizontal direction, that will keep varying from can vary from layer to layer, but within the layer the properties is assumed constant. So let me erase this here. Okay, so what you have is the half space, layered half space. Now when we say the SSI system, let's say your foundation is situated on a layered half space, then in that case these are the systems which you can have. It could be embedded, it could be on the surface, or it could be fully embedded and partially embedded. When we say structure, that means the structure consists of foundation also, as we discussed in the last lecture, and this is the case where typically foundation is supported by pile foundations. So piles are there, and the top of that you have a structure. So these are the systems, and in all these systems you could see that your structure is situated or embedded inside the soil, and situated on the base of the structure is situated on the soil layer, a particular soil layer, and at the end of the soil layers, what is called, this is called half space. So it is called layered half space system. So continue with this. So what you have is, now coming to that, what are the direct and substructure methods of the analysis for SSI analysis. In direct methods, what you do, you consider some part of the soil, the structure itself, which is shown in this figure, and analyze together in one go. That means here you need to understand that you are analyzing the structure, including its foundation, with the some part of the soil, which is again layered half space system. That means it is assumed that both structure and soil are bonded together. There is a no, we are not uncoupling them. Okay, so in this case it is called direct method. But when you deal with the direct methods of analysis, the problems occurs that you may not, because the normally you deals with structure and soil with the different packages, or even within the same package, the type of elements which are used in finite environment is different for structure and soil. And normally in the structures, you require a lot of detailing compared to what you have in the soils. So we can make the layered model for the soil, but it is not possible to make a layered model for the structure. So what is done here in this method? So this is broken in two parts. One is called free field. With these are the circles where the later on this structure is embedded, and you have another part here which is combination of that structure only. Here I would like to emphasize that there are two types of nodes here which you could see. The hollow circular nodes are denoting those nodes which are lying on structure soil interface. That means these nodes will be common to both structure and soil, and in fact the soil and the structure communicate through those nodes, and these are the communicating nodes here, while you have the solid nodes here which are exclusively only the structure. And in this method, no node is considered inside the soil. Okay, this is only at the boundary where both are embedded. So now continue with this. So this was the direct method. So what you do here, that you carried out free field analysis, that assuming there is no excavation and no structure on the top of it, then carrying out the free field analysis, you can find the motion and in these nodes, that is called soil amplification. Okay, and this was the case when you are not considering any structure or foundation on the top of it. Now when you want to put the structure on top of it, then what you need to do, then you can replace this portion using what is called spring and dashboard can be replaced by this portion, and the motion which is found in the free field is applied here. So now the structure can be analyzed as before, as means you can go in so much detailing as was used here, and here spring and dashboard will be representing your missing soil or scattered motion. Okay, so this way we can find, once this modeling is completed, then you can find the response as early as possible. Continue with this. So this was direct method on the left hand side, and you have what is called on the right hand side you have this what is called the substructure method. So now let's discuss the next part of this. What is the effect, beneficial effect of SSI? Now normally your structure might be situated on different types of scenario. It could be situated on rock or hard soil, that is type first. It could be situated on medium soil, type second, and soft soil. So this is what is called response spectrum for a typical single degree of freedom system, and this figure is taken from IS 1893. So what happens, normally the presence of the soil makes the system flexible, as we discussed, and thus decreases the natural frequency, or there is increase in what is called natural period. When the natural period gets increased as before, normally after increase in the natural period, you come in this range. Okay, let's say this is the value of time which is equal to 0.4 seconds for rocky side, but for soft soil it is 0.55 seconds. So let's say natural period is increasing beyond 0.55 seconds. As a result, whatever increase you have in the natural period, it will decrease. If you go on the right hand side, then this will decrease the value of SA by G. That means when it is more flexible, then the accelerations, seismic acceleration will decrease. So normally acceleration for the structures which are founded on soft soil is smaller than that for the structure which are founded on rock. So this is beneficial effect of SSI. However, in general, SSI leads to smaller accelerations and stresses, and thereby smaller forces in the structure. But this sentence is qualified by with in general. That means in most of the cases. So it means SSI may lead to smaller acceleration However, there are numerous documented case histories where the perceived beneficial effect of SSI have led to the oversimplification in the design loading to unsafe design in foundations and superstructure. So this will lead to unsafe design of foundation and superstructure. So this what is called this beneficial effects may not be always present. Rather, there could be the cases where the SSI may lead to the larger response. So it should not be always assumed that SSI will lead to the smaller forces in the structure. Now, when we talk about SSI analysis or normally in soil interaction, what we do, we come across a term what is called dynamic stiffness or impedance functions. So this is the same thing. Let me write down it here. This is dynamic impedance functions, and this is also called what is called dynamic stiffness. So dynamic stiffness. You have a static stiffness, and this represent this is exactly the same thing. Whether you say impedance functions, dynamic stiffness. Second part, dynamic stiffness. Once you have this dynamic stiffness, the dynamic stiffness in this case is given from this relation here. But before we go in the dynamic stiffness, let's talk about equation of motion for harmonic excitation. Considering viscous damping in the system, equation motion of harmonic excitation can be given from this relation mu double dot plus cu dot plus kstu, where m is mass, c is damping coefficient, and kst is static stiffness, and that should be equal to the applied load. So once you have here, because for harmonic excitation, you can write that u is equal to u naught e I omega t, and pt force can also be represented p naught e I omega t. Once you put these numbers, then e I omega t will be cancelled out from both sides, and what is u left? U naught multiplied by k minus m omega square plus ic omega should be equal to p naught. Okay, so the p naught is the amplitude of force applied. So in this case, what we could have that, because when you are considering viscous damping, then this k, which is nothing but p naught by d naught, can be defined by kst minus m omega square plus I omega c. Here k star is called the complex dynamic stiffness or impedance functions, and this will be static stiffness minus mass multiplied by the omega square, that is the omega, where omega is the angular frequency of excitation in radian per second, and c is damping coefficient. If you are, instead of viscous damping, if you are considering static damping, in that case, for static damping, the effect of damping is found out what is called the correspondence principle, and in the correspondence principle, that the damping is damping coefficient will be represented in terms of static stiffness. That means to find the effect of damping, you require static stiffness. So here, damping is taken care by this term, that is kst 1 plus twice iota zeta minus m omega square. Now, if you compare the two forms of equation, which is one is for viscous damping, another is for static damping, then you can find that I kst twice zeta, which is coming from this equation, should be equal to ic omega. Okay, that means c, damping coefficient, can be found out twice zeta divided by omega into kst, where zeta is the static damping ratio. And once you can see that means c, damping coefficient, is proportional to kst number 1, and of course damping ratio is coming in picture, and angular frequency is also there. So this way, once you have find this damping coefficient, then you can use this formulation also. But normally for the soils, static damping is more popular, and because it is verified with the experiment. Now coming to this static dynamic stiffness or complex impedance functions, this dynamic impedance may be represented in a general form, that is in two parts, K star equal to KST multiplied by K1 plus iota K2, where KST is static stiffness and K1 is the real part of the stiffness and K2 is the, once you have this multiplied by imaginary part, so that means imaginary part of this. So here, if I compare with this above equation, K1 is nothing but KST minus m omega square, while the value of K2 could be either omega c or it could be twice zeta KST. So this way you can have a comparison between what is called viscous damping and static damping, and when we discuss in the next lectures, which we are going to talk about what is the difference between the different types of damping, and that is very important for the soil. So this is most of the material has been borrowed from this book, which is titled Dynamic Solution Introduction, Prentice Hall, Eaglewood Cliffs, University, USA, published in 1985. And this, as mentioned in the last lecture, that this is very fundamental book on soil structure introduction. Thank you very much for your kind attention.